Let me begin by thanking the quantum space-time group for giving me the opportunity to talk here, and for once I'm on the other side. This is based on the paper that we put out on the archive exactly 2 weeks back, and it concerns the much talked about Jackiw-Teitelboim gravity and rotating black holes. Jackiw-Teitelboim gravity has become important in the recent study of the broad class of models which are known as the SYK like models, and their putative gravity duals. So, this talk is going to be about that. So, here is a brief outline of my talk. At first, I will discuss a quick review of JT gravity, then how one gets JT gravity from charged extremal black holes, and up until now it was not at all clear as to how the Jackiw-Teitelboim model correctly reproduces the dynamics, or more precisely the thermodynamic behavior for extremal black holes. At first, I will show how this works for non-rotating black holes, for which the arguments are crystal clear, and then we'll go on. Then we'll go on to rotate, extending the arguments for rotating black holes, and then as a check of our analysis, I'll discuss two explicit examples. One is rotating black holes in 5 dimensions, and other is rotating dionic black holes in 4 dimensions. So, let me start by discussing the Jackiw-Teitelboim model first, although this will perhaps be obvious to most of you, but it will still be useful just to set up the notations and conventions. So, Jackiw-Teitelboim gravity was explored by these two people, Teitelboim and Roman Jackiw, in the 80s, and has been explored in its many avatars since then. Yeah, it's Claudio Bunstein now. Yeah.
This is a whole story.
Yeah.
Only over lunch.
Yeah.
Okay.
Yes.
All right.
What was their motivation? Was the S-wave reduction their motivation, for studying this?
Well, I have not studied their paper in detail, but they were, I think, just trying to look at some simple models in 2D.
That's a good question. We should read the paper.
Yeah. So, here's the
Teitelboim has thought about these nearly topological, like
yeah.
easy.
So, his the title of his paper is Gravitational Hamiltonian Structure in 2-Dimensional Systems.
It's like where you don't have any local dynamics, but just
Yeah.
So you need one scalar with gravity.
Yes. In the full talk, I will just be talking about Euclidean gravity, and here's the Euclidean JT model, which is described by this action.
Suppose I added a del phi square also to this Lagrangian.
Yes.
How would it change the theory?
Yeah. So, del phi square can always be brought to this term by a suitable Weyl transformation. In fact, as we will see, that's actually crucial in obtaining the JT model in this form. We'll see a moment.
It would change the constant behind the phi?
No, behind, so this R phi thing won't change. The R phi because in 2D, because of the rigid structures of 2D, there's no such thing as Einstein frame or different Weyl frames. The coefficient before R remains the same no matter what Weyl frame you go to. You can only get rid of the kinetic terms by a suitable Weyl transformation.
The field redefinition of G.
Yes. Yeah. So, this is the Euclidean JT model. Yeah.
Mollison and Stanford Yang also write the topological term.
Yeah, they do, but we are just considering the linear piece in phi, and for our so the topological piece won't be relevant for our discussion here. I mean the
In thermodynamics it is.
yeah, I mean in thermodynamics that just gives the ground state entropy, or the if you are talking about the free energy, the full topological term will just give you the mass at 0 temperature, but so we are just thinking of deviations above extremality. Okay, I'm going a bit far ahead, but okay, this is the action that we are dealing with. And as we all know, in 2 dimensions, gravity has, from the traditional counting, -1 degrees of free.
Sorry, just
yeah, sure.
IGH is forced on you by the usual considerations, right? To have a principle of least action, including boundary term.
Yeah, this one, yes.
No choice.
Yeah. So that's just for a well-defined variational principle, and there will be one more counter term which I'll come to shortly. So this is the action that we begin with.
G tilde is a two-dimensional.
Yes, this G tilde is a two-dimensional Newton constant, and which is dimensionless. And we'll discuss this specific in a moment. And so with additional scalars, the system has 0 degrees of freedom. So the whole thing is described just by the boundary theory, which is just here, and it's sometimes called, including by Malleson, Stanford and Young, the boundary graviton. And this boundary is all, sure, no, obviously.
Yeah. So let me look at the bulk first.
Yes.
If I remember right, the bulk solutions have 3 parameters.
Yeah.
So what do you do with those 3 parameters?
Yeah, so these 3 parameters correspond to 3 SL2R elements, and you can bring by any some suitable SL2R transformation. For example, this phi, the solution of phi will have 3 parameters, and you can choose some SL2R transformations to bring it to this form, where Z is the traditional Poincaré coordinate.
So you've got these 3 parameters.
Yes.
But the 3 inequivalent solutions, I would say physically, are either this linear dilaton.
Yes. Or time dependent.
Or a black hole. Or the third solution is one which has a singularity
Yes.
on the 2 Poincaré horizon.
Yeah. I mean, the phi most general solution in the Poincaré coordinates would be something like, let's say, alpha beta t plus gamma t square minus z square. Because we are Euclidean, it might be plus or minus over z. So this is the solution we are looking at with beta and gamma set to 0.
And then the 3 correspond to the discriminant, that is beta square minus.
Yes.
Or something like that discriminant.
Yeah.
I think, discriminant literally, right? Beta square minus 4 is here. So,
Yeah.
taking various values, 0
Yes.
plus 1 minus, right?
Yeah.
How are these related to the SL2R? Why are these parameters SL2R?
No.
How are they related?
Okay. So let me say this. So, okay, if you go to some, if you do some SL2R transformation on the coordinates, it is possible to reduce it. I mean, okay, so for certain value, for certain conditions, to go to this form.
I mean, let's put it like this. You always have a killing isometry, which is
Yes.
preserved. And just which isometry is preserved, there are various inequivalent
Yes.
isometries, is determined by phi.
I see.
Yeah.
So
So,
when phi is 1 upon Jesus,
yeah. No, I'm sorry. Yeah.
then it is in Poincaré coordinates, then d by d Poincaré is preserved.
Yeah.
When it is of a form which we are calling is the black hole, then d by d Schwarzschild time is preserved, etc., etc. So
Yeah, and so more precisely, this phi actually breaks. So in ADS2, there's an SL2R isometry. This phi breaks the SL2R isometry down to U1. I mean, only one combination of the SL2R generator. I mean, for example, in this case, only one of the SL2R generators, let's say, just del T, that generator will annihilate this, and the other 2 won't annihilate this. Del T will annihilate this. Yeah, so SL2R is broken down to U1, and so
Acting by the broken generators generates beta and gamma.
yes,
So just to be sure that this choice
Hmm.
where you have just alpha,
Mm-hmm.
and let's say another choice where you have alpha and gamma both
Yeah.
live and alpha equal to minus gamma.
Yeah.
So that's physically distinct.
Yes.
And that's
yes, that's the eternal black hole solution. Yes.
The other one is something in which of the plus
Yeah, so
Yeah.
there I think you get a null singularity.
Yeah, I mean,
yeah, so that is something in which the dilettone vanishes.
Sorry, not to derail, but just if it's physically distinct, how can it be both generated by symmetry and be physically distinct?
I don't think it's generated
No, no.
by symmetry.
it's not generated by
But I
symmetry.
thought if you act on this solution with the symmetry generator, you get.
You get that. This is
Yeah.
correct.
So then how can it be physically, it's some boundary condition business? How? It's physically distinct if you maintain the same boundary conditions.
Yeah.
If you also transform the boundary conditions,
Yes.
it's not physically distinct.
Yeah, I mean, here the
But
no, I'm sorry. Go ahead. Yeah, here the boundary conditions are all important because the whole thing comes from the asymptotic isometries of ADS2. So therefore, obviously, demanding different boundary conditions will give you some
So in particular, the boundary conditions, at least that we worked with, and Maldas and I all worked with, and might be interesting to ask if there's a wider class of boundary conditions. But anyway, the boundary conditions looked at are Dirichlet for phi.
This.
So the dilettone takes a certain value at the boundary, and then as you say, that of course is not invariant under an SL2R. So fixing the boundary condition to be phi equal to say phi b. If you now take a different solution in the bulk, then you have a physically different situation. Or to put it another way, there's just different choices of boundary.
Yeah.
So
Starting with the same state in the boundary and making a conformal transformation would then be dual to these solutions.
Oh,
Say
yeah.
that again.
Yeah.
Starting with the same state
with
as the
this
boundary.
with the state corresponding to this particular boundary condition, and then
Yeah.
making conformal transformations.
They will in general be different because the conform I mean in this case okay, let me just go to the next slide. This J parameter actually measures how much conformal symmetry is broken. So in the presence of this linearly varying dilettone, there's no conformal symmetry in the sense that any arbitrary diffeomorphism does not keep the action invariant. However, what does keep the action invariant is the left coset action of the SL2R, where you can just let's say parameterize the boundary time, and you can at most have some SL2R ambiguity in the transformation of this boundary time.
Put it another way, because of this linearly varying dilettone, you're actually breaking conformal invariance.
Means the full one, the local one, or you,
I mean, you're breaking
the
SL2R.
yeah.
So in that sense, your boundary theory also doesn't have SL2R symmetry as a symmetry in theory, because the bulk dual doesn't have the isometry. But having said that, if you still carried out the conformal transformation, then yes, that will correspond to this transformation. But it won't be a symmetry of the boundary theory, which is not conformally invariant.
Not of the state, right? The state is not invariant, but you can transform the state by this.
I mean, in the, let's see, in the spirit of ADS CFT, the isometries of ADS correspond to the symmetries of the CFT, right? I mean, that's why we say we have a symmetry, because here you don't have a, the analog of ADS itself breaks the SL2.
What about setting all constants equal to 0? That's also a solution.
Yes.
That's right.
Yeah.
That's right. That's
Yes.
right. There's also a solution.
Yes.
Morally speaking,
I mean,
And you give an added plus constant there, right? To this.
No, I mean in
oh yeah, you can always, because that's like just transforming the
yeah, yeah,
the
right,
state.
yes.
Yeah. So you could meet your boundary conditions with that?
Yes.
With just that.
With just phi equal to constant. That's correct. That actually is, literally speaking, just the grounds. From the point of view, at least of a higher dimensional extremal solution, that's just the topological theory, where phi is 0 or whatever, phi is some constant, and
You've gone all the way into the.
you've gone all the way. But then you can't consider any finite energy excitation, excuse me, in that theory, because they are singular.
Because it preserves the SL2.
Yeah. In the moment you want to consider any finite energy so that theory, state is just the ground state, states of the system.
Yeah.
For any excitations, you have to take the linear.
So the whole phase space consists of one point plus all of this.
So, if I may make a comment, in this theory, the equation of motion for phi actually does not admit a constant solution apart from 0. Yeah, because there's a grad square phi, grad mu phi plus a g mu nu phi term. So, this particular theory does not admit a constant solution. So, whatever constant you have, that will go into the topological part. Yeah, so the the equation of motion for phi, I am not being very careful about the signs here.
You're
Yeah,
right.
plus g mu nu grad square phi plus let's say yes.
Because he has adjusted things.
So it does not admit any constant dilaton solution unless it's identically 0.
Yeah, okay, you're right. You've chosen phi equals 0 so that you're getting the entire
Yes.
topological piece.
So the whatever shift that you have, it just goes into the topological piece.
Okay,
Yeah.
So in a sense, you made some canonical choice.
Yeah. So there are two limits. So the boundary, as I said, is specified. So we are working in this 1 over boundary where phi is 1 over this script j z, and this z equals, so phi equals constant means we are choosing a boundary at z equals zb, and we are interested in the region where the temperature is small enough, meaning this second condition here. So that should apply for any JT model, not just for theories reduced from higher dimensions. However, for ZB is the location of the boundary in the Poincare coordinates, wherever the boundary is located. And for theories which are obtained from reduction of higher dimensions, for example, extremal black holes, we impose this additional condition that 1 over ZB should be much less than the energy scale J. So that comes from higher dimensional theory, and that is to ensure that this phi is much smaller than 1, and we can actually truncate it, let's say just at linear order. If we are okay, I'll go into more details in a while. If let's say this phi were much comparable to 1 and or much bigger, we'd have to written all terms in, much higher order terms in series of phi. So that's why we don't. So to approximate the near horizon geometry of extremal black holes well by the JT model.
These are additional. This is not so much internal to JT
Right.
model, but now in a situation that JT arises,
Yes.
the low energy limit of
Yes.
complete geometry.
Yes.
You want the separation between temperature and
Yeah.
the conformal breaking scale. That's what
Yeah.
Sorry, but just back to the JT model, your boundary condition then completely fixes the location of the boundary in your solution, right? There's no freedom in that.
correct.
Yes.
So I thought the theory had boundary degrees of freedom, which you
Yeah. So yeah. So but the boundary degrees of freedom would correspond to small reparametrization of the time coordinate, and this if you let's say went something like t your time and define to t plus epsilon t, where epsilon is a function of t, you would get an action which involves just this extra infinitesimal transform. That's one way of looking at it infinitesimally, but in general there's other way where your boundary is defined by let's say the proper time along the boundary, let's say the whole proper length along the boundary, and then as has been shown by Maldason, Stanford and Young, the full treatment of the boundary proper time actually gives you a Schwarzian action on the boundary, while this one gives you an infinitesimal version of the Schwarzian.
I'll be very stupid.
Yeah,
I'm asking
okay.
a very stupid question, I know. But in your original coordinate system, the boundary was completely fixed, right? There was just
Right.
that coordinate system, there was was one point in phase space. Now you can do a coordinate transformation if you want, and then we can debate whether that is real or gauge or not. But how can it change the action? I thought the whole action was invariant under coordinate transformation.
Small let's say Shiraz, you did the SL2R in the bulk, so now phi instead of being 1 upon jz became that more complicated function. Now you still demanded that phi is some fixed value at the boundary. Then this new boundary is not the same as the old one, no matter which coordinate system you describe it in. That is, okay, one way to say it is this: let's fix our coordinate system once and for all. Then we have two solutions for phi, one upon jz and one of the other ones. And in both of them, we take the curve, boundary curve, phi equals phi p. These will be different loci in z and t or whatever.
In z and t, but the one loci is mapped to the other by a coordinate transformation. Because phi was constant, it remains constant. I mean, that is, you have to fix, yes, under a coordinate transformation, one boundary will have a different description as in terms of an equation. In terms of an equation.
And another, but the two boundaries will not become the same.
But isn't it the same manifold? I'm really sorry.
No.
I've got a manifold, and I've got a boundary. On that boundary, phi is constant.
Yeah.
Now I use a new set of coordinates to describe that. It's true that in the coordinates the boundary would be different, but it's the same manifold because we're finding that same constant value is physically mapped to the same point.
Yeah, but that's not what's happening here.
Oh.
You have two different boundaries.
Why are they two different boundaries? I thought you take my first solution. It had a boundary at phi equals constant. Then I do a coordinate transformation. My new solution still has phi is equal to the same constant. So isn't that what this boundary mapped to under the coordinate transformation? Because phi was constant.
Okay.
A particular constant.
This is true that on shell.
No. Not on shell, just as a statement of
Okay, just to say very simply, take two solutions. Huh?
Yes.
Phi equals J1 times 1 upon J1z and phi equal to 1 upon J2z.
Whatever J2z.
I mean, just two different, this is a simple version.
Z goes to alpha z.
Now, take one fixed coordinate system just to compare things.
Yeah.
One is one straight line somewhere, the other is another straight line somewhere different. So, these are two physically distinct points in loci in space-time.
In the z coordinate.
In the z coordinate, but if
and different values of the z coordinate.
Right, but there's a certain proper distance between the two. It takes some proper time to go between the two.
But if I took the first solution and I did z goes to alpha z, it maps to the second solution, including the boundary going to the boundary.
It does, but this is one of these symmetry breaking things. It's because you've broken a symmetry by the choice of boundary. You can move this boundary to another boundary through this transformation, but it's a physically different.
Yeah, I mean, okay.
Sorry.
So, just to put it in
Please to fix your coordinate system once and for all, and then examine if it's the same points in space-time.
I'll ask one last question and then I'll stop. Suppose I just imagine evaluating the action. In the action, I'm just doing the coordinate change. Why isn't that action invariant under the
Because it's not a small
Morphism.
different.
Yes.
It's a large
Morphism.
different which
Yes.
changes the value of the action. It's because
Yeah.
of the K term.
K. This term always remains 0.
This will also happen in gauge theory.
The-
Because there's a partial integration that you keep doing, which is allowed for small gauge transformation, but not for large gauge transformation.
Yeah, I'm just not seeing here why you have to do any partial integration in my changing the coordinates.
I think it's simpler than that. I mean, it's.
Yeah, I mean, to put it in another way, I mean, I'm just borrowing terms from Maldassana, Stanford, and Young again. The ADS2 breaks the asymptotic isometries of the boundary theory spontaneously. So, there's no action associated with it. It's just a family of 0 modes. This varying dilaton breaks the SL2R and breaks the asymptotic isometry explicitly with the scale. So, this explicit breaking of symmetry induces the action.
Yeah, is something happening at the horizon at the other end? That would help me understand. If it was utility and sounds to me that what I'm saying is right. But I'm probably saying it. I'll ask you later.
Okay, sure, yeah.
Okay, you can also say it as an active versus a passive.
I just like to see, like, you take an expression and you do the coordinate change.
Correct.
How is the action changing?
Yeah.
But but seeing that the physical location of the boundary changes
Yeah.
is easy to do by fixing where our rulers are and asking for a fixed ruler, are you here or there? You know.
You're asking with this with two separate theories, right? Because the two theories have two different values of j.
But the two different values of j can also be thought of as two different solutions for the same.
I suppose that's the point.
No, I mean just in terms of coordinate transformation.
Probably the point. Okay.
Just in terms of coordinate transformation, to answer your question, if we demand that we also have another set of
Different theories are simply choosing different scales, as you see.
so Z, let's say I'm calling this T hat code.
I mean, you can say it like that, but it's, I mean, you can say it like that, yeah, you can say it like that, but it's a simpler thing. I mean, this is just a statement, is it the same physical boundary or not?
Yeah. So just to be clear about the coordinate transformation question that you are asking, if we do this coordinate let's say we have a Poincare T and Z, and if we demand that there's an asymptotic symmetry of the boundary, so asymptotically as Z goes to 0, the metric under a small change of this time parameter, the metric continues to remain Poincare in the let's say in the Pfefferman-Graham gauge, then this epsilon parameterizes the infinitesimal time deparameterization. And if you just blindly put it in your action, you will find that so I'm at this stage I'm doing everything at the linear order. You will find that it has acquired an action something like this on the boundary.
I suppose I just need to go through this calculation. I'm sorry.
Yeah, sure.
Just one question. I mean, if you have a manifold with a boundary, then all diffeomorphisms of the manifold which were allowed before, I mean, all diffeomorphisms of the manifold will not preserve the boundary. The boundary will, will wiggle. For example, if you look at the, this what happens also in conformal field theory with the boundary. All conformal field theories on the plane, okay, are not allowed when you have the x-axis as the boundary. So it's a subset of those which are allowed. So similarly, with diffeomorphism of a manifold with the boundary, there are diffeomorphisms which will physically change that boundary. The boundary will change physically.
It's certainly true that if your diffeomorphisms don't die out and so on, they'll change.
That's what I mean.
Yeah.
Absolutely. But I mean, the simplest thing is the following: the boundary is a one-dimensional locus in 2 dimensions, and you can specify it by defining a bulk function and saying it has some value.
Yes.
If I'm allowing yourself different bulk functions, I'll surely be able to generate different boundaries this way. You know, that's the root. That's the root.
And the only confusion is that how do you know the two bulk functions are actually different?
Yeah, how do you know they're different?
And because one is related to the other by coordinate transformation, it doesn't look different.
Yeah, yeah. So, okay, so
I
then
mean, we can just
we should, but I mean, my dumb statement would be fix a coordinate transformation. So how do you check, given two scalars, how do you know they are different or the same? You know, you fix the coordinate system you want to use, and then ask, are the two scalars taking the same value at a given fixed point? Okay, or not? You know, I mean, that's okay.
So it turns out that the action as stated in the previous slide, it diverges when you just try to evaluate it on shell. Therefore, to get a finite action and also finite mass, you need to add this particular form of the counter term to the JT model in the previous slide. So it's this and this. And the on-shell action, as we have been discussing now is a boundary term which just involves a Schwarzian derivative, and the mass is also related to this Schwarzian derivative. And the free energy of this system is given by this quantity. At the low temperature, free energy is just goes like T square. And the crucial things to notice is that there's this G tilde appearing in the denominator as well as the J, and G tilde, as I said before, is a 2D Newton's constant, and J is the parameter that just measures the breaking of the conformal invariance. And this G and J, when we are talking about extremal, near extremal black holes, they are determined from the higher dimensional theory, where this G tilde is related to the higher dimensional Newton constant and the volume of the transverse space of, because for a near extremal black hole we would have something like AdS2 cross M, where M is M is what I call the transverse space, and it depends on its volume. And the scale J actually comes from the variation of this additional of the scalar field, which corresponds to the volume of the transverse space.
Sorry, what is the calculation that gives you that F is equal to T square?
The on-shell action.
On-shell action, how do you fix T?
Yes.
Is it Euclidean space?
Yeah, this is all along in Euclidean space.
Okay, so you're in Euclidean space, you make time periodic,
Yeah.
and then you evaluate the on-shell action for that.
Yeah. And
on-shell action being the Schwarzian.
yes.
Being the Jackiw-Teitelboim. original.
Yeah, right. And this, yeah.
So this is not Schwarzian of T of tau, but Schwarzian of tan.
No, I'm yeah, for general okay, in the Poincare time.
So I'm saying that from the first equation to the second equation.
Yeah, okay, right. That's right. Okay, so I was just making a quick compendium of things that should come later. That's definitely right.
Gautam is saying a particular T as a function of tau is chosen.
Yes.
The other way around to get that, right?
Right.
That is dictated by the black hole.
Yeah.
And what it does.
Yeah.
to the
Yeah.
bound.
Yeah.
Yeah, so the T that he said here is to be thought of as the replaced by tan of pi.
That's right. That's right.
And then
That's right.
So a particular function is fixed by your choice of dilettante solution.
Yeah. Yeah. I mean, you have to.
In terms of x coordinate, boundary coordinate.
And the value of the dilettante, the fixed value of the dilettante doesn't appear in your...
Fixed, yeah. So fixed that comes from G. So it's a renormalized free energy. Whatever that 1 over ZB dependence that you had, that gets cancelled.
Sorry, can you show me again what G tilde was?
G tilde was the
Does just G tilde know about what value you're fixing the dilettante to be?
no.
So that value does not appear in your final.
So this is a very important point. I mean, the precise value doesn't appear,
Yes.
but the scale
Scale appears.
J appears.
Yeah. So solution, but not value.
Yes.
Exactly. So it's one of these ADS things that, you know, once you are in the, once you have this region which is asymptotically ADS to, then it doesn't matter exactly where you are.
And
Of
yeah.
course, you're not going to compare with SYK, I presume. But
Yeah,
if
no.
you did, then here you'd identify G tilde to be 1 upon n. Right? I mean, roughly speaking, after some imaginary.
Right. And although this is not important, but there's a possible ambiguity of a rescaling symmetry which comes when you just let's say scale Z and T both to lambda and J in an opposite way. The theory remains the same, but in order to compare with the UV theories, we just take our definitions in of the higher dimensional temperature to match with the lower dimensional temperature to fix this ambiguity. And now I'll describe as a review how the JT model arises from charged extremal black holes. So this is the extremal Reisner-Nordstrom ADS geometry. We have the black hole horizon here, and this red region is the infrared or ADS2 throat, where the metric assumes this form where it factors into ADS2 cross S2, sometimes known as Robinson-Bertotti space-time, and there's a constant electric field in this region, and this is the asymptotic ADS2 screen, and this whole blue region, as we just go farther from the black hole horizon, the metric assumes this form, and there's the final asymptotic ADS4 screen over here. And let me now describe how we get the JT model from the reduction. So this was also done by earlier papers of Sandeep's, and including one in which I was part in these two papers. We dimensionally reduce the Euclidean Einstein-Maxwell action with a spherically symmetric reduction ansatz like this. And you will notice that there appears this factor phi naught over phi, which is precisely designed to cancel an unwanted kinetic term for phi in the effective 2D action. And the full reduction of the 2D action gives this term with one scalar, gauge field, phi and graviton, and with it is a boundary term. And now I would like to make an important point that we are always working in the canonical ensemble. Namely, we are working in an ensemble in which the free energy is just given by E minus Ts. And when we are working with canonical ensemble, we need to work with a fixed electric charge, and if you just want to get the full action, just the canonical free energy from the partition function, following Stephen Hawking and Ross's work in Simon Ross's work in the 90s, one needs to add an additional boundary term to the theory, which is evaluated at the same place as the Gibbons-Hawking boundary term. This additional boundary term ensures that we are working in a sector of fixed charge. Shall I proceed? So here's the sort of recipe to obtain the JT model from the 2D action that I had flashed on the previous slide. We put the gauge field on shell. So, and in this talk, for the purpose of this talk, we are not considering any other fluctuation in the gauge field. Namely, we are not considering the so-called phase mode in the SYK model. And we put the gauge field on shell, and this phi as
large gauge transformations associated.
who? Yeah, that's right.
So this is SU2 or U1 gauge field?
U1 everywhere. So this is so we expand this field phi, so about its attractor value. So this phi naught that sits here in front is the attractor value of the solution, which just corresponds to this fixed near horizon geometry. But we want to just see the deviation from extremality, so that's why we have to deviate from the attractor value.
But is it clear when you put the gauge field on shell, some boundary conditions, when you evaluate the action, there is no action for the reparameterizations of the gauge field? Is that clear? Or one has to do this to see that?
I mean, okay, you want to say something? No, yeah. So we are always working in a particular sector where the gauge field variation comes with just the variation of charge on the boundary, and we are always demanding that we are working in a fixed charge sector. Therefore, we have explicitly constructed something to get rid of any unwanted fluctuations. I mean, it can be done, obviously, the additional fluctuations of gauge field, as was done in our previous paper, but for the purposes of computing the free energy, here we are neglecting this subtlety.
The real story is that, in fact, it turned out to be quite subtle to understand the action of this phase.
Yes.
And initially, I mean, Gautam the idea was that just as here the Schwarzian corresponds to these asymmetric, asymptotic isometries, the phase mode should correspond to sort of gauge transformations which are large. But actually it turned out to be more subtle, and in a case where say you have a near horizon geometry which is of this ADS2 type connecting to asymptotic infinity in 4D or higher, the rest of the region also plays a role. So it is not just near horizon data that goes into giving a finite action, etc. for the system. So it turned out to be a little thing. It's true that morally speaking, those degrees of freedom are associated with Wilson lines that extend up to the boundary, but in fact also care about what happens. So it turned out to be a bit of a story. But okay, here he's not going to change the charge just to keep
Yes.
Yeah. Well, my question, so the phase mode indeed, as you explained, but even more simply, the question was that what about the reparameterization of the boundary? Do the gauge fields contribute to the action at all?
for the
Reparameterization.
I understand your question. I mean, the answer to that is not directly. That is, once you write the Schwarzian action down, then that's the whole action.
Yeah.
There's nothing, no additional cost even.
Yeah.
That's because you fixed it with a fixed charge, or?
Yeah, so I mean that's an interesting subtlety in like he is mentioning, which is that under a reparameterization, it's the phase mode that couples with the Schwarzian mode to give you an action, and that's quite non-trivial. But however, that does not arise, as is evident from our earlier work, when we are working considering no fluctuation in the gauge field.
Yeah.
Because
had you allowed the charge to change, then there is an interesting coupling.
Yes.
Between the reparameterization.
Yeah, then this epsilon mode, which is the Schwarzian mode or the time reparameterization mode, that couples quite non-trivially with the phase mode.
So there is a coupling between the
Phase mode and the Schwarzian.
Time reparameterization mode and the phase mode. So the
Right.
sigma model gets modified when the time reparameterization mode.
That's yes, yes,
Exactly.
that's right.
That's right.
Yeah,
We'll show that
Yes.
in such they were told also, I think.
yeah. But since we are considering I mean, deliberately just putting the phase mode, ignoring the phase mode, that situation does not arise here, is what I would think.
So you are not considering the coupling between the sources?
No.
Or rather, that coupling is not important if you
Yeah,
keep
yeah.
the
Theta is 0. What theta we call the phase mode. We are taking something so explicitly to set del theta to 0. We are just restricting our attention where there's no fluctuation of the phase mode.
I see.
Or no phase mode at all. That's
that degree of freedom doesn't.
Yeah.
It doesn't
So,
change.
so
It's
you're
constant.
tuning mu appropriately to achieve that. I mean, how are you doing that? I mean, it's just there.
No. I mean,
Sorry, Al,
Yeah,
what
sure.
Upamanyu is trying to do is probe the thermodynamics in a restricted way, in the following restricted way. He will keep the charge fixed, so he'll work in the canonical ensemble and simply evaluate the free energy. In the fixed charge sector. And in that case, that phase mode is fixed to some value, and you don't have to keep track of how it changes with the temperature.
But the charge is not just the constant mode. You can have variant modes or not. Keeping the charge fixed.
it's a
It's like a angle degree of freedom, which then just is at a fixed value,
Yeah.
theta dot or whatever.
in fact the way actually we have set it up, it works point by point, where the variation of the charge is 0 at each point on the boundary.
But if you vary the action is like mu f prime plus theta dot whole square. Right?
Yes.
So let's say you make theta 0.
Yeah.
This mu f prime term.
Okay. You are worried about the constant piece?
Yeah.
Okay.
That takes a
Yeah.
fraction from f
Yeah.
the boundary.
Yeah. So this whole boundary, this also has, this ensures that that is also taken into account. So, just I think the analog would be something like the topological term that arises in the JT theory, and this is rigged to cancel that term as well.
Yeah, you're right. At zero temperature, there is a answer to the free energy and an answer to the Gibbs free energy and so on and
Yes.
so forth, which you can compute, and they will differ by charge-dependent terms. But here, what he's asking is, okay, I am taking the free energy and I'm heating up the system, keeping Q fixed. Okay. Now everything depends for this fixed value of Q on the temperature, and can I compute that temperature dependence? This is the question he's asking. So there is a wider question which you can also ask, but
Yeah.
you know,
And at this moment, we have concentrated on just that very admittedly restricted question.
Because if the grand canonical form,
Yes.
this term,
Yeah.
I mean,
Yeah, yeah, yeah.
U square F prime square.
Yeah.
What you were calling T.
Yeah.
there will be
So
U square
that will indeed come. That will indeed be there. So when we linearize this action with this form, when we linearize in phi, we get precisely the form of the JT model I had mentioned in the first slide. And we read off from the full solution. So this coefficient that appears here was minus 1/16 pi g tilde. We read off the g tilde from there, and our big phi was just r, the radius, and from there we read off this energy scale j, and therefore the JT model gives the correct free energy.
So let me
Yeah.
just see where each term came from.
Yes,
So the phi r came from the Einstein term.
yes,
of the original
yes,
code. The phi constant.
yeah. So this,
that came from the sphere.
yeah. So this came from a very non-trivial combination of all of this.
From the cosmological constant.
Cosmological constant, the sphere, and also from putting the gauge field on shell. That's actually quite necessary to get the JT model action.
Yeah, because we need to expand around the solution.
Yes.
exactly.
Yeah. Okay. Fine. And the boundary term you put by hand.
No, this boundary term just came from the full 4D action, including the Gibbons-Hawking term. Nothing into. So this boundary term we added by hand. This, if that's the term you're referring.
The boundary term that appears on the next slide, that came from this.
Yes. No. Okay. Yeah. So the boundary term actually cancels. I mean, makes a non-trivial contribution to the bulk term. Okay, you want to say something? Okay.
I mean, as you said, if you go back to the previous slide, you know, the Gibbons-Hawking term in 4D is dictated by the bulk term. Now, if you do things consistently, if you're going to get the Gibbons-Hawking in with the phi in 2D, you're going to get the corresponding. But it actually comes after.
But is this like like two boundary terms? One the UV boundary, and the other one is the
That's a great question, and so okay. At this point, it should be added to the UV boundary as well, just to get the full.
but then when you do the S2 reduction,
Yeah.
it's the far off boundary. That's probably
Yeah, I mean, so you have actually spoiled my next punchline.
No, but
Yeah.
this is the near horizon action because
No.
go back to the
Yeah, this is the near horizon.
because you're expanded.
Yeah, you're all.
So
Yes.
So really,
So
what
the four-dimensional Gibbons-Hawking therefore should be sum of two Gibbons-Hawking terms, as I imagine you should.
Yeah,
Because you have one UV boundary,
and one IR by.
IR boundary.
Yes,
Is
and
that the way you
yeah, I'll just come. It will be. It's just my next slide if you.
But algebraically, you could compute the action of the four-dimensional solution cut off near the horizon. and
Yes.
get it straight.
Yes. Yeah.
that's I thought what you were saying.
Yeah.
So it is only the IR boundary.
Yeah.
You don't care about the weather. You don't care about
Now then he's going to justify why this is correct and so on. Why was it okay to put the
Yes.
the boundary term in this region? So that
Yeah.
go ahead, sorry.
So there was the next slide, which was this, and this is not true. What I just said is not true because of this.
What is not true?
so I blithely said that I just linearize the action, get this, get the G tilde from here, get the linear variation from J. So, but in saying that I cheated a lot because that's simply
In saying
not
what? In evaluating the value of the action.
value of the action, and even in evaluating the full action itself. That's
But
not true.
It's correct for cutting it off.
Yeah.
If you want to cut it off, right?
Yeah, so the thing is that this phi, this is true only when little phi is small. So when
So you shouldn't in particular expect to get the right value of the action. Because that's contribution of the action.
yes, yes, yes.
Okay.
Upamanyu,
Yeah.
I had a question.
Mhm.
So just for parameter matching with this thing,
Yeah.
tilde will be n,
Hmm?
n plus n,
G tilde will be 1 upon m, okay.
and j is just the symmetry breaking parameter.
Yes, yes.
Both of them contain RH.
Yes.
So
So they
why
come.
is n and j being scaled?
Okay, okay, okay. So very good question. They come from two different things. So the volume of the transverse, so our phi is just the volume of the transverse sphere. So this phi is the volume of the transverse sphere. In G tilde, so you can write R as RH time 1 plus, do you agree? So this RH is, so this G tilde in other words is something like 4 pi phi naught square, and this is phi naught, the attractor value of the geometry. And this one is the deviation of the fields phi, and this one parameterizes the deviation from the attractor value. And R minus RH, when we write it in the Poincare coordinate, is simply L2 square over Z. Therefore, this becomes phi naught 1 plus L2 square over RHZ. This
I think I understand the computation. I'm just saying that both of them involve the same scale.
yeah, I mean it just turns.
Maybe we put it another way.
Mhm.
So that about the phi naught, okay, which you are not keeping, of course.
Yeah,
But suppose you did keep that phi naught, just the phi naught term.
yeah,
Then you will get the topological term.
yes.
Multiplied by RH square by G4.
By 4G4 in fact.
Or whatever.
Yeah.
So RH square by G4 then
Hmm.
will have to be identified
Hmm.
with just n, right?
Hmm.
Because that will give me the zero temperature entropy.
Mm-hmm.
And so the d2x integral will be some topological term, that's
Hmm.
just a number. So it, and I know independently that is just n times log 2 or
Okay, 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 okay. I see, I see.
so that stuff, RH square divided by G4, that's getting here,
Hmm.
that will have to be n.
Okay, 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 okay. I understand your
Now
question.
it
Okay.
seems
Hmm.
that RH is also being related to
Yeah.
J.
Yeah, so let me just do it the n scaling. Let me just do it for asymptotically flat case, then it will be clear.
G4, right? Only
This L2 square is RH square. So in other words, our G tilde, let's work in asymptotically flat case, G tilde will be 1 over RH square and J will be 1 over RH. And if this is n, this will be square root of n when our
No, but the more important point is that you have another parameter which is n plus square or g.
Yeah.
Right. So that's why you have two independent parameters. One is j and one is n.
I mean,
So that is coming from the G4, is that right?
yes,
Exactly.
yes. So there's one.
When you think about it, that there's a ground state entropy, which is a number, S naught, which is n or n square, whatever, and then there's j, which is a scale, a dimension of.
So so you were saying there are three length scales in. Sorry, I'm taking.
Mhm.
So there are three length scales in the gravity problem. One is the Planck length, another is the ADS scale,
Yes.
and then the black hole radius. So out of which I can construct two dimensionless objects.
Yeah.
And presumably those are the n and j.
Yeah,
Yes.
or if you like, yeah, j then in units of.
Mm.
Oh, sorry. J has to be, of course, in units a temperature, then I have two dimensional space. One is beta j, other is n.
Exactly.
Yeah.
Right.
Yeah.
Now,
Yeah.
so that gives me 4 scales in reality, because that's
That gives you 4 scales.
Mm.
But as always in ADS, the ADS scale is a scale, but it doesn't show up in physical quantities because of the isometries of ADS.
I see. It just
I mean,
doesn't count.
it shows up either in the central charge, but that's the coefficient of. Yeah, it's similar.
All right. Okay.
Yeah, so obviously this in particular, just by equating the full thing, and I say, okay, G is this, that was way too fast, and obviously that's, and it's only at this stage, it's a coincidence that it's giving the correct answer. But is there should be an argument as to why it's giving the correct answer. So here it is. I mean, just to motivate what I'm going to discuss next. So this is the black hole horizon and this is the asymptotic ADS2. The full JT model action, which we are claiming is the correct free energy, comes just from this infrared region.
And for the statement to even make sense, it's totally crucial that it didn't matter where you got it off. The value of phi naught.
Yeah, provided that certain of these inequalities are satisfied.
In this
Yeah.
region.
Yes.
Because otherwise the statement that the action that gives the right value would
Exactly,
meaningless.
exactly. And the full low temperature free energy or the full low temperature free energy above extremality is coming from the full action evaluated right from the black hole horizon to the asymptotic ADS4. So it looks like it's by some sheer magic that the two answers are agreeing. The question is, what is this region doing? So that brings me to one of the most important results of the paper, how JT exactly gives the correct thermodynamic behavior for non-rotating black holes at first. So let me be more precise now. So this is the full action, which is from the horizon to asymptotic infinity for the Rn case, obtained from reducing the full Einstein-Hilbert action with the additional boundary term of Hawking and Ross. So this is the full dimensionally reduced action. And now what we do is we split this full action into two parts. So this is just just the time direction just comes along for the ride, and we are just let's say talking about the r direction, and we split it up into two terms so that there's one integral from the horizon to the ADS2 boundary where we cut off the JT model, and then there's another integral which is the integral from the ADS2 boundary to asymptotic infinity. And now we on the ADS2 boundary we rig up the boundary terms, including the required term for going to the canonical ensemble, in such a way that this term, when we linearize this phi and do the usual stuff, it just gives me the bulk JT action, just phi times r plus 2 over L2 square.
Because in that region you can linearize.
Yes, in that region I can linearize with impunity. But if I were to linearize all the way, I couldn't have done that. So this is the first claim, that we are actually.
Wait, I didn't quite. The boundary action that you add here has to be cancel the boundary.
Yes. We add and subtract. Yeah, add and subtract.
You add and subtract. You've already told us what boundary action you used in JT, right?
Yes.
You just do the same thing.
Yes.
Word it in foreign language.
Yes.
Which you could because
Yeah.
it comes down from that.
So this is the first step. Now yeah.
I'm being pedantic, but
Yeah.
in the first step, you're writing the boundary term
Yeah.
only at infinity, and not
Yes.
another boundary term.
This is that. Okay. This is the full counter term required to make the full action finite, the full Einstein-Hilbert action finite, obtained from the horizon to asymptotic ADS4 infinity. So this is the full action that gives us the correct results, correct free energy, correct mass, and so on. For instance, this would be something like the Balasubramanian-Krauss boundary terms at infinity. Yeah.
with the
Okay. So at this one,
Yes.
okay, this asymptotic. So this again I'll come to.
Euclidean, this is the horizon Euclidean?
Yeah. So over here we,
Euclidean.
yeah. So we impose strictly Dirichlet boundary condition, or at least some fall of, okay, no, not strictly Dirichlet, fall of condition.
There's no boundary.
There's
as
no
such.
boundary.
Okay.
already.
Okay. Yeah. Okay.
Okay, so Euclidean. Okay.
Yeah.
Okay. Just to not get too lost in the details, if you just focus on the point you were making, which I think captures, there's a Gibbons-Hawking term to begin with, but it's at infinity.
Yes.
Right. Now, when Upamanyu described the JT model, he had a Gibbons-Hawking term at the boundary of the asymptotic ADS2 region.
Right.
He said, where did that come from, right? But what he's saying is, I'm going to add and subtract the Gibbons-Hawking term
To this part and this part.
to this part and this part. Now, one part becomes JT, the rest I'm going to make some argument about. Okay, so that's the.
So okay. At this point, I'm not even thinking about the Gibbons-Hawking boundary term on the ADS2, and in fact, we'll see how that emerges from and
Okay, that's
yeah.
one way to
Yes,
put
yes,
it, or
yeah.
you could have put the Gibbons-Hawking or right
Yeah.
whichever way, but
Yeah.
right,
So I mean, I'm sorry, I didn't understand one comment that you made that it's Euclidean. There's no idea, but I mean in R there's always a boundary. It's not like it's S2. RT is not. I mean T is S1. It's I would like to think it's S1 cross R.
The S1 shrinks.
No, S1 shrinks. I mean, you're talking about the horizon just. Okay. Sorry. I got that wrong. Sorry. At the horizon, S1 shrinks. Sorry.
That's all. So
Yeah. I thought you were talking about the asymptotic infinity boundary. Sorry. So we just get after. Okay. So this is the far horizon integral, the so-called far horizon integral, which is evaluated from the ADS2 boundary to asymptotic infinity. This is the bulk piece. These are the boundary pieces at the asymptotic infinity of ADS4, and this is another boundary term that's added to get agreement with the canonical ensemble. This is on the ADS2 boundary. So notice the two symbols that I'm using. So this infinity it just stands for the ADS4 infinity, and this del stands for the ADS2 boundary.
Yes. So K is not needed in the del boundary?
K, okay, yeah, that's what I'll be coming to. Okay, so here are a number of steps that I'll describe before I state the final result.
So just to give us a
Yes.
roadmap, you're going to show that this is zero, right? Presumably.
I'm going to show that the finite temperature deformation of the far horizon integral generates precisely the variation of the Gibbons-Hawking term and the counter term on the ADS2 boundary,
Which is the statement that this part is zero.
which is the statement that the contribution from the upper part is does not matter.
Is zero?
Yes. The under a temperature okay, up to some certain. So I'll just show you
It's zero or
some boundary term.
The temperature derivative, mu derivative, these things are.
Yeah.
But if you're going to get the right free energy, it might be zero.
Yes.
That's
Yes.
why, I mean,
Yeah.
one way to put it is if you had added and subtracted at the boundary of the ADS2 region, the relevant Gibbons-Hawking term, so that the near horizon region part became literally the JT model.
Yes.
The rest would be zero.
Yes. Yeah. Right. That's the way of saying.
I see. I see. There is no contribution from the other thing
At all.
Yeah. I mean,
Answer from this part.
yeah.
Other thing, or to put it in,
I thought it was a constant and the derivatives are.
I'll show you.
nothing. I mean, the temperature dependence is all correctly coming from this.
From just from this region, from the ADS2 throat,
But
or
the
particular.
value itself of the free energy is.
No, that's a more complicated thing. The ground state entropy comes from just the horizon value, but that's more complicated. Here he's only talking about the departures. The temperature dependence.
Temperature
is low
dependence.
temperature.
Yes.
Let's put it
Yes,
like
I
that.
see. Yeah, so therefore, like temperature derivatives are agreeing between the ADS2 and the ADS4.
Yeah. Right.
At low temperature.
Yes.
In the T
Yeah,
over
at
T.
Yes.
Correct. Exactly.
So we just hit the system up a little above extremality. So here are a number of steps, and due to this variation, the bulk term, which extends from the ADS2 boundary to the asymptotic infinity, because we are just perturbing about the extremal solution, which is an equation of motion, this bulk term vanishes.
You're going to show that the variation, as you change the mass of the black hole,
Yes.
the change in this contribution is
Yes. Yes. So this variation under, let's say, del G, or under all the variation of the possible fields, just vanishes by the virtue of equations of motion. So there are terms generated on the asymptotic infinity, but we take fall off conditions so that they fall off fast enough at the asymptotic infinity. So this just goes away, and there's this term on the ADS2 boundary, and since we are working, as I have mentioned before, working in the sector of fixed charge, the variation of the gauge field actually cancels this term. So in the fixed charge, this term also vanishes. So what happens is that the full variation.
So if the boundary terms vanished by themselves.
Okay, yeah, there's one boundary term that's being generated on the ADS2 boundary, which is coming from the variation of this term, this bulk term. When you vary this, so because this R piece, when you vary this, the derivatives will hit on phi in some way, and it will come there.
It's not doing this adding subtracting.
At this point, no. At this point, I'm just doing some calculation, just our good old calculations.
The other piece is not quite what you wanted.
Which other piece?
I
Yeah.
correction to various form.
Yeah, so I'll just show. So, these are some of the things I just said. So the only non-vanishing term just comes on the ADS2 boundary, and it involves only the dilaton, phi, and the metric. And interestingly, because we are on the ADS2 boundary now, where this little phi was assumed to be small enough, we can actually linearize the big phi on the ADS2 boundary.
Sorry, just
Yeah.
I was spacing out. The kappa term at infinity doesn't contribute.
What kappa term?
Extrinsic curvature.
Oh, at no. Okay, so when we vary this, we get something like our let's say the Brown-York stress tensor. I guess that's the name, delta G mu nu.
Exactly.
And this delta G mu nu, we are assuming boundary conditions that they are falling off fast enough towards the asymptotic infinity, so that this has no contribution. Or I mean, I don't want to say strict Dirichlet, but let's just say certain fall off conditions, so that this contribution, we assume this condition of them under a master. Sorry.
We know what delta G mu nu is. It's 1 over r to the 4, or whatever, 1 over r to the. And it's not that this is exactly of the form that contributes.
If it's a purely normalizable deformation,
Yes.
so the given sorting term is usually rigged up so that for Dirichlet boundary conditions, you would not have a additional boundary term. Here it's not exactly Dirichlet, but if it's purely normalizable, it cancels out.
But it's just if we just take a black brain and ADS, isn't a large contribution to the on-shell action just from the square root GK?
For T mu nu, you get it. What you're saying is that
For instance, if we were in flat space, the whole contribution is from square root GK because r vanishes.
Yeah, but for that I have the counter term. You see, it's k minus 1 or something. The counter term makes the
I thought the counter term makes it finite.
Makes it
That's
finite,
a
yeah.
Stress tensor.
Yeah.
So, like in a conformal theory, that is what gives you the
Yeah.
temperature to the power 4 or whatever that is. Just from that k minus the counter term piece, I mean that was the calculation of the renormalized stress tensor.
Yeah, I thought
Yeah.
my memory was that a large contribution of the answer comes from the square root GK. Shantini, it's right. Yeah.
let me see. We thought it does cancel.
Yeah.
Let's go back and think about.
So again, some charge business maybe?
No, not really. Not for this, I think.
Or maybe against part of the bulk index. The volume also increases.
Right, okay. Let's see. So, I mean, mean, the first thing is that we are interested in the change to first order in the
Yes.
perturbation. If you change the mass and you
Yeah.
change the metric. And we are expanding about an extremal solution which is already on shell.
Yeah.
So the corrections to the action can only come from boundary terms.
Yes.
Then the boundary contribution at infinity from the bulk action cancels exactly the boundary, the Gibbons-Hawking contribution. And at the ADS2 boundary,
Yeah.
if you had added the Gibbons-Hawking term, it cancels the
Yes.
Gibbons-Hawking term. You know, this is the structure of the argument.
Yeah.
So there's an increase in the volume near infinity. When you say the boundary contribution, the bulk part is just some volume. There's a volume in the square root k part. You're saying that you're holding something fixed so that the volume is changing in such a way that the kappa term changes. It cancels it.
You know, maybe, okay, roughly the structure of the argument is the following, that, so okay, suppose we change the mass a little bit.
Yeah.
And we think about it as changes in various components of the metric.
Yeah.
Now, near the horizon, the change in the metric due to a small change in mass is never small. You know, because the, say, GTT vanishes somewhere and then it doesn't vanish. But if you are sufficiently far away, that is from the asymptotic ADS2 region to infinity, then it's a small change. The perturbations are really perturbations everywhere.
It's small.
Okay, and what we are interested in is the first order change in the action. Okay, now since the zeroth order solution you start with is itself a on-shell solution to the equations of motion.
Yeah, it comes all from the boundary.
It all comes from the boundaries.
Right.
That is, the contribution to the bulk action, in effect, can be written always as just boundary terms. Now there's also a contribution from the boundary term you're adding, namely the Gibbons-Hawking boundary terms. What you can show is that the contribution from the bulk action that is also writable as a boundary term cancels the Gibbons-Hawking terms on both sides. That's the structure of the Gibbons-Hawking.
Now I understand. This would also, would this work just for a black hole in flat space?
Yes.
It's a very general.
Yes. It's a, for all black holes.
Not necessarily asymptotically ADS.
Yes, asymptotically flat black hole.
Wait, so now, suppose I had a black hole in flat space without doing any cutting off or anything, just the whole thing.
Yeah.
Have you just argued that the action is independent of temperature?
The catch in the argument is that the metric is not a small perturbation. It's not a first order. You know, I use something here in a very.
Suppose I make a small change in mass. I take a black hole solution of mass m and change m by m to delta.
Near enough to the horizon, that is never a small change.
Yeah.
Okay.
So what I used here was that I have an action as a function of the metric, which I expand as g bar plus delta. And delta g is always small compared to g bar.
Now
In the far horizon region.
So the fact that the action can be computed by throwing away a region is actually a general phenomenon.
Now I understand. So you're saying everything comes from the tip of the cylinder in some way.
Yes.
In some way of thinking.
Yes.
When you have an asymptotic ADS2 region, you can make it very precise.
Yeah.
That's
The-
the point.
Stress tensor is exactly equal to the K root gamma.
I mean,
The-
actually,
Yeah.
probably make it
Exactly
precise
equal.
in a.
No, I mean this is sort of the definition of pi mu, if you like.
You know,
I mean not just the k, including from the variation of the r term, it generates this pi mu nu.
You're saying that this cancels with the Gibbons-Hawking term.
No, this I never said that. I said that we are assuming fall off conditions del j mu nu, so that it vanishes on the asymptotic infinity. That's the only statement. I did not say it cancels. I'm just imposing some boundary conditions on this.
It seems to me that you've added. I'm just rewording what Sandeep said. You've added this boundary term so that the variational problem works also at the boundary. So then
Yes.
the fact that the bulk contribution to the action changes under the first variation also, there's nothing special about the boundary. The boundary contribution also changes under the first variation.
Exactly.
As long as it is a first variation.
Exactly. That's right.
Yes.
That's right. Sorry. That's exactly right.
It's very nice.
So that's only boundary condition that's actually imposed on the ADS2 boundary is the one mentioned in the first slide, which is a strict Dirichlet boundary condition on this field phi. And
Oh, sorry, can you say what you just said?
Yeah.
I didn't hear. What is a strict Dirichlet boundary?
condition on this little phi on the ADS2 boundary. There are no other boundary condition, I mean, except that certain.
From this point of view, you're choosing to your cutoff here, so
Yes.
that phi is constant.
Yes. And
there is
yeah.
I don't know, I'm coming back, sorry,
Yeah.
leaving my phone, I'm very sorry.
Okay. So here's the variation of the far horizon integral that I had written down in this slide can be written as these two terms. So this is the Gibbon-Socking boundary term on the ADS2 boundary. This is the counter term on the ADS2 boundary needed to make the JT model finite, the JT action finite. So these are the two terms. However, we also get this complicated additional terms, and it would only work if they vanished, and the answer, as you have guessed by now, it does. Therefore, this is one of the key results. The variation of the full action under a small temperature deformation is the variation of the full JT model action with the counter term, which gives the correct thermodynamics. Therefore, this argument shows why JT model produces the correct thermodynamic behavior it does, because in some non-trivial way, the far horizon integral ceases to be relevant or ceases to be important.
But this non-trivial way didn't really require calculation.
So this not, I mean,
It's a very beautiful statement, but I think it doesn't really require calculation.
no, I mean,
It's just the fact that the variation of the action, including the two boundary terms, is constant, including changes on the boundary.
I mean,
It's zero, including changes on the boundary.
Is zero on the, there's one small caveat which we haven't gone into, which is it was important that the ADS2 boundary is located at a constant value of phi for this. That turns
Yes.
out to be a little
Y-
important in there.
yeah.
So that you could use the JT part.
So yeah, but even from the far region, so that you could use the fact that the variation of the bulk action, which is a boundary term, is exactly what the Gibbon-Hawking.
Yes.
Why isn't that guaranteed? I thought the fact that the variational principle works, including changes, including
No, I
changes
mean,
on the boundary,
so
will make it work.
I mean, may I say just say something? So this full flash before your eyes is a full integral, and this does not turn out to be identically zero. These two terms, this turn out to be zero after we impose specific form of the metric. I mean, if it were, I mean, if it,
Not identically zero, but suppose you impose that it was a solution to the equation.
yeah,
Then it should be zero, right? Because I thought, maybe I'm being stupid, but I thought the whole logic of that boundary term was that it ensures the variational principle works also for variations of fields on the boundary. And therefore, therefore the same argument you use that it can't depend on the bulk also works for the on the boundary.
That's a little bit strong, I would say.
Yeah.
The logic of that term is that it gives a well-defined variational principle.
Including for variations of the field at exactly at the boundary.
No, but with Dirichlet boundary conditions.
Ah, you say
Yes.
with variations on the boundary with particular boundary conditions.
Yeah.
Okay, thank you.
yes,
That is the point.
That's it.
Now it turns out that here what happens
Dirichlet boundary conditions for phi.
uh,
Or also for induced metric.
yeah, in general,
Yeah.
let's say Dirichlet boundary conditions for the metric. Let's
Okay.
put it. Now here what happens is that if you look at first the ADS2 boundary,
Mm.
since the metric is becoming asymptotically ADS2 there,
Mm.
it's in effect Dirichlet boundary conditions for the metric.
Mm.
But the dilaton is growing. So for the dilaton, it's important that you impose effectively Dirichlet boundary conditions.
Very nice. Thank you.
That is why the boundary condition of JT arises to get the equality. And at infinity, things are effectively dying. So it's effectively.
So in the first part of the JT gravity, that boundary term was coupled with a particular boundary condition.
Yes, yes, yes.
And it's, that boundary condition is rather important because the dilaton grows actually.
Yeah.
Yes.
So the phi equals constant is really crucial. That's
Yes.
a well-defined variational principle.
Yes.
With this boundary.
Yes.
You know,
Yes.
So then you need that surface.
That's another very important point. That's very. That is, if you just done the analysis of the JT model, then the boundary term you add actually gives a well-defined variational principle with this boundary condition.
Yeah, that's exactly what you're saying.
Yeah,
Right? And
yeah.
therefore, you have to use this boundary.
Yeah.
And
Okay,
then-
thank you.
And then once you've done that, there's no calculation.
So I have, I think, half an hour left strictly. Yeah.
But I think
Yeah.
that's an important point.
Yeah. So this variation of, and I would say that it works rather non-trivially because this does not immediately follow from the equation of, I mean, at least I am not able to see in a very transparent way. Maybe it does, but I think this.
I'll just say one last thing.
Yeah.
I mean, it's great to check with calculation, but once you've decided there is a certain set of variations under which there's a principle of least action, including boundary variations.
Yeah.
If you perform only those variations, it's guaranteed to work without a calculation.
Okay.
And that's what you're doing, right?
Yes.
And therefore, it's guaranteed
Yes.
to work.
Yes.
Now, the calculation is good for a check.
Yeah.
But there was
Yeah.
logically, it had to work.
Yeah, I mean, when you impose, I mean, it's obvious from this formula, if you impose effectively Dirichlet on the metric as well, this will definitely vanish.
Yeah, but I think
Yeah.
Shiraz making the point that have you made sure that including the boundary term, the action would have been invariant, then you're guaranteed that, say, the far region is not going to contribute.
Yeah.
So there's a certain class of variations for which that's true, and if you sure you're putting it in that class, which I think you're doing, then logically speaking, you couldn't have.
The boundary that you're referring to is the ideas 4 1, the ideas 2 1.
The whole thing.
The whole
Because
thing
you
with
put the
the
boundary
two
term here and here.
For the outside
Outside.
part.
One of the things is that a crucial point is that even the ADS2, as Sandeep kept emphasizing, that the mass deformation is not a small deformation in the near horizon region.
Yeah, this is a very
Yes.
good. I hadn't realized.
And this delta GAB, therefore, I mean, it can't be treated as effectively Dirichlet, and it just turns out from the equation of motion, from the way of the way the mass deformation works, that this vanishes. I am sure there will be some more subtlety to it.
It's two different things. In the near horizon, it's not a small perturbation, but at the boundary, which
Yeah.
is far enough away,
Yeah.
the delta G is dying out fast enough.
Yeah,
It
yeah,
lies
but
in the class
of-
of deformations for which you have a good variational principle. So
yeah.
had you been able to regard it as a small perturbation, it would not have contributed in the inside region either. But
Yeah.
you can't regard it as a small perturbation there.
Right.
Whereas in the far region you can.
Right, right,
That's the
right,
structure of
right,
it.
right, right.
Well, Shiraz's argument is saying that first order variation
Yes.
coming from ADS
Yes,
to ADS.
yes,
But
yes.
aren't you going to say that in the small low temperature thing,
Yeah.
it's not just T square, but the next terms will also.
No, we don't get the next terms.
If you don't
Only
get
T
the.
square. Only T square. In fact, you can see for next term what happens is the further breaking effects.
Yeah.
because It will go like T cube over J square.
I see. So
Yes.
T square is just always first order only, so it nicely matches with.
Yes, yes, yes.
So I see.
Yeah.
That is actually the argument.
Yeah.
we give.
Yeah, sorry. That is
That it's the
argument,
first.
yes.
I mean, it's
First order.
crucial that it's first order.
Yeah, delta M is T
But
square.
then, as he says, no calculation is required because the
Yeah.
first order variation being 0 is
Yeah.
the principle
Yeah.
for.
If you like, we are just making sure that the Gibbons-Hawking term
Yeah.
is the correct one for the first order variation. That's really what the argument is. It doesn't use
The details.
the details. As long as the decays are of this type. And
Yeah.
Nice.
Should I proceed? So these arguments go through for any general dimensions ADS D plus 1, and the 2D action reduces to the JT model with these parameters, and also gives the correct free energy. I don't think there's anything more to mention here. But
Sorry, just
yeah.
I see. So this is the relation between
Yeah, the relation from the UV.
parameter. So RH is related to J through L square.
Yeah.
G4 okay, all right. I'll digest that.
Yeah, so this is the volume of
information.
yeah.
Capital L is here.
The ADS length.
ADS.
Hmm.
So this is
Yes.
if you're in ADS D plus 1.
Yes.
So this is the ADS4.
ADS D plus 1 length scale. The RH is
I'm treating D as 4 here. I mean, or whatever.
yeah.
I see. All right. Okay.
Now we can consider most general theories in for black holes which have some ADS2 horizon and ADS2 near horizon region, and we can obtain a general form of action like this with, let's say, multiple gauge fields, some potential for the scalar, and some other additional scalars. The important thing here is this phi to the d minus 1 piece, which is just the transverse volume, and it's with the linearization of this term that we obtain the JT model.
What does this statement that you just showed mean for boundary CFT? What kind of statement would it?
I'm not sure. I'm not
Which
sure.
boundary?
The three-dimensional boundary and the effective treatment of it as one dimension. I mean, the free energy of the 3D boundary being reproduced by some effective quantum mechanics, right?
I'm not sure. Yeah, that's a very interesting question, but I would be interested.
Sorry,
Yeah.
I understand the question. Sorry, so you're saying, yeah. So you're saying take an asymptotically ADS4 black hole. So then you have a 3 plus 1 boundary, and then is that
2 plus 1 dimensional boundary.
Oh, 2 plus 1D, yeah, sorry, 3D, and then you come in the near horizon and it's a 1D boundary.
Yeah,
So why is it
your
being
somehow
reproduced?
statement is that three-dimensional free energy is being reproduced by effective
Yeah,
conform field theory.
yeah,
I mean,
that's
Yeah.
right,
conform field.
that's right, that's right. And yeah, what is that 1D conformal theory? We don't know, but roughly speaking, the idea is that the radius, that the transverse two directions go to some fixed value in the attractor region. So it's you have the KK modes in the extra directions, which are fields of appropriate conformal dimensions here in the near CFT. And you can see that from the bulk also through the dimensional reduction and map the dimensions and so on. But of course, it would be nice to work out an explicit example where this happened.
So it's not too surprising, right? You put a conformal field theory on S2, at low energies it becomes conformal quantum.
And here it is very similar to that. And,
Good, yeah.
but it would be nice to work out some.
course.
Yeah. Because it's a very generic feature.
Yeah, but this is not a statement about low energies, right? This is a statement about free energy. It's temperature dependent.
Getting your
Low temperature free energy.
So the statement is that you start with your
I see. So in that sense, from an RG point of view, it's not very surprising.
yeah. I mean the statement is you start with a 2 plus 1D CFT on an S2, but then in the presence of some chemical potential, which is a scale, and then you go to temperatures much lower than the chemical potential, then there's an effective one.
Yeah, the chemical potential is crucial, otherwise you'd have a mass gap and you'd have length.
So from an RG point of view, only low energy degrees should contribute, which is effective going down in dimension.
What's interesting is that this low energy theory is this special kind, this conformal quantum
Yeah,
mechanics,
conformal.
broken
Yeah.
conformal.
Yeah.
That's sort of
It's a very universal structure in terms of generalizing the idea of CFTs, at least in quantum mechanics, that near CFT. I think it's very interesting, just to understand it from that point of view, I think would be sort of interesting.
Yeah.
So universality of for general CFTs.
Yeah.
This first order is bothering me a little bit because in SYK,
Yeah.
I could. So what I'm doing is like conformal perturbation theory around J equal to infinity. Okay, and I actually have double expansion, of course, in terms of n and beta j. So well, let's say leading order in n. So n goes with some structure like beta j plus 1 plus 1 so I can actually crank that, and I can go on. Okay, of course one might say that GT captures only the like 1 upon beta say
Yeah.
in the beta f term.
Yeah, it's a sort of, that's right.
I see. So I see. So I can go on,
Yeah.
but only the t square term.
Yeah, exactly. For the rest, you
So if
the higher order.
here in principle, of course, you could go on to other terms, but then there is no guarantee that it will have anything to do with SYK, and
Or
or
even
even whether it's universal in some way.
In fact, you don't expect it to be universal.
Yeah. So ADS 5 and ADS 4 will give you different things and such like.
It won't just be the scale J that will enter. All kinds of things will start.
Yeah.
So that's it.
Yeah, that's right.
So, in this general type of theory, the only one subtlety is that this could potentially generate some additional boundary terms on the ADS2 boundary, but for the I'll just mention now that they turn out not to be important, and I'll just move on quickly to the next part.
So everything, this
Yes.
argument generates.
Yes.
This argument
Yeah.
goes-
So now is the question as to how JT.
There's one important thing to emphasize there. If you just go back to
Mhm.
that other thing, in general, you have in these black holes, say that you get in string theory many scalar fields.
Yeah.
And you have in extremal geometry, you have an attractor phenomena that fixes all these scalars. And then when you look at the leading deviation away from
Yeah.
the horizon, various scalars run. It is
Yes.
not just the
Yeah, and they run with.
and they run with different scales, but the important scale that enters in the free energy in T square over J is the running of the transverse field.
Yes.
That is the
Transverse
preferred
mean,
Whatever appears in the.
radius of the S.
Yeah.
Rather mean transfers to ADS2.
Yeah. So this is the volume that appears in front of the two-dimensional Ricci scalar. And so now.
So that's
Yeah.
interesting. So you say that there are other scalars that break conformal invariance in some other way, but that doesn't show up in the
Yes. Yes. Yeah. And
Sorry.
No, no.
Is actually
no. Yeah. So in the leading order free energy, they turn out not to be important, and I'll give you the argument later. But let me just proceed.
But
Yeah.
just to say, sorry,
Yeah.
but it's a peculiar property about the free energy at
Yes.
constant charge. If you were looking at the susceptibility, charge susceptibility, etc., then all the other scalars enter. And it's not only
Yes.
the leading near horizon theta then. It's more interesting.
Yeah.
The moment of inertia and so on depends also on the asymptotic.
Right.
So it's a richer story, but this is very universal, and it's tied to the Schwarzian action coming out as generic. Okay. Sorry.
No, it's okay. So now is the time to demonstrate how JT gives the correct thermodynamic behavior for rotating black holes. But before that, what's the trouble?
One last question.
Yes.
These additional scalars in this JT model would just be minimally coupled scalars? Would be additional.
Yeah, we'll see an example soon if you.
They are scalars corresponding to various mass. Can also have some mass terms.
Yeah.
Mass terms that minimally coupled, but no coupling to R.
No coupling. Exactly. So the only thing that couples is.
one resultant scalar
Yeah.
which couples to R, whose running determines.
Yeah, I should have.
Be coupled in some
Yeah.
sense. All right. Okay.
Yeah, I should have put this in red or something. So for rotating black holes, what's the trouble? The trouble is obviously that there's no straightforward reduction that we can do, as in for the Rn case, and there's a non-trivial theta dependence lurking here, because this sigma is theta dependent, this rho square is theta dependent, and the dimensional reduction is obviously not straightforward, at least. However, there's an important observation that when you are looking at the volume of the transverse space of the space transverse to this space, I mean whatever enters in the entropy, that's this square root of sigma. That usually I haven't explained what sigma is, but most of you definitely know the form of the Kerr metric. And the thing is that sigma exactly when you are talking about an extremal black hole near horizon, that's just a constant. And also the leading departure away from it does not have a theta dependence at all. That's in fact, that's the first hopeful sign for our endeavor, because that's precisely the term, this little phi term, that we are interested in. So that's an observation. And there are some more observations. The near horizon Kerr metric, as was shown by Bard.
Sorry,
Yeah.
but Upamanyu, I would just say that the transverse sphere,
Yes.
its volume is obtained by doing the theta phi integral.
The theta, yes, theta.
So
Yes.
the only thing it can depend on is the radial direction.
Yes, indeed.
And I thought this theta dependent, this warping thing,
Mm.
in Kerr metric at least,
Mm-hmm.
if you go to some rotating frame,
Yeah.
then it sort of becomes a sphere, because the angular rotation has all kinds.
Yeah, I
of
mean, they're.
precisely at the horizon, it just becomes a S2. But what you have to do is to take, instead of phi, you have to take some phi tilde, which is like phi tilde minus something times t. And in terms of that phi tilde, it's just d theta square plus sin theta.
No, actually, that's
It
what
doesn't happen
people
that
do.
way.
Unlike ADS3, no, it doesn't happen because
Yeah.
the rotation in the curve
No.
actually squashes the geometry. So
There's no.
it's very interesting. This is the paper that was written with Ashok and so on. That you have an attractor phenomena even for extremal rotating black holes, but the geometry is not doesn't have the S2 isometries anymore, right? Because it's broken. But nevertheless, the entire theta dependence is determined by the attractor phenomena. So it's a little bit like all the partial, the full
Yes.
YLM
Yes.
can be thought of as scalars in ADS2, which are fixed by the attractor. So
I didn't know that you had it's watched.
Yeah. So the near horizon Kerr metric takes this form, and this has an ADS2 part, which is our sort of holy grail by now. And this geometry has the required SL2R isometry. And in this paper by Sandeep, Ashok, and others, it's been shown that general extremal rotating black holes display this attractor behavior, and they also considered some black holes in string theory as well. So motivated by this and this following observation, will make the following claims. In the far horizon region, finite temperature perturbations to the metric and the gauge field components are all small, just like in the previous case. Because
there's no. Is there a notion of an S-wave reduction in this case?
will come
it's
to.
much trickier because
Yes.
the higher partial waves will all make.
Yeah, I'll show you the dimensional reduction in a moment in the 4D case. Yeah.
So your derivation of a 2D, are you going to derive a 2D theory?
Yes.
Okay.
So the S wave reduction is more tricky in
Yes.
the sense of a KK. Nevertheless, if you're
Integration.
if you're simply interested in a much more restrictive question, which is compute the on-shell action, you
Yes.
always say, I'll first do the theta phi.
Yes.
Yeah.
Yeah.
That's the restricted sense in which we
Yeah.
Morally, there's probably some KK analog, but it's not very useful.
And in the near horizon region, as was flashed in the previous slide, we have an ADS2 behavior, the SL2 and the associated SL2R isometries, and also an attractor behavior of certain of the fields. And the claim is that variation of most of the metric components can be taken to be small in this near horizon region. As an example,
But not all components.
yes, most, but not all. That's why I highlighted the most. For example, in the full metric, so this is something that appears in the Kerr metric, rho square is r square plus a square cos square theta. A here parameterizes the angular momentum, and if we are working in the sector of fixed angular momentum, it turns out that delta A has to be non-zero. A has to be changed.
As the temperature.
So delta A will go like a temperature square.
A is like angular velocity, some parameter.
Yes. So J is m times A. And for finite temperature deformation, this del rho square, it goes like T square. And this del rho square by rho square, this variation when we are working in sufficiently small temperatures, this is small everywhere. Right from the black hole horizon to the asymptotic infinity we are integrating to. And the crucial input that will come in the later dimensional reduction is that the near horizon dimensional reduction has to be consistent with the symmetries and the attractor behavior. And near the horizon, for example, this rho square assumes ceases to be a function of r and becomes only a function of theta, namely r. This r square goes to, so this goes to an attractor value called rh square plus a square cos square theta. So this is our claim, and this we claim will give us the correct free energy of rotating black holes. But now you say, what's the proof?
What will you do? I haven't understood.
The claim is we are doing a dimensional reduction in the near horizon region with an ansatz that's consistent with the near horizon symmetries and the attractor behavior. And we are claiming that the far horizon integral under a finite under a small but finite temperature deformation will whatever terms it generates will just be the boundary terms on the ADS2 boundary.
Yeah, its variation will vanish again.
Yes.
Fine, but I haven't understood what the near horizon.
Yeah, I'll come to it. It will be best illustrated with an explicit example, if you will.
But basically, what he's arguing is that there are some perturbations in the metric which can be regarded as small. If there's a perturbation in the metric which can be regarded as small everywhere,
Then it
cannot contribute to first order. So we throw those away. Now, what remains are perturbations in the metric which are small in the far region, because that's always the, but not small in the near region. For he is going to keep only those perturbations in the metric and do the theta phi integral
Yes.
and compute and get it 2D action, which will
Yes.
be of the j theta.
And
Yes.
with the boundary term.
Yes.
And
Yes.
how you, the boundary term will be whatever the UV boundary term.
And the IR boundary term.
And
Yes.
on the IR boundary.
Yes. So the question is whether I mean, so this was
So, basically, these modes are just those modes that move the tip around, right?
That moves the tip around.
yeah,
That's
right.
And the dilaton, because that's coupled to these modes. See, because
Yes.
the action is fine.
Yeah. So the because the dilaton couples to these modes, the running of the
It's very
dilaton.
simple, actually.
Yeah.
Yes. So now your question is, okay, that's a very general abstract argument, but does it work?
So, is there a Schwartzian way of getting the same thing also? This is all, that this near horizon part is some Schwartzian?
Yes.
That's the point of throwing away these other ones.
Yeah, exactly.
Nice.
After you do that, then it's a short.
Nice. Nice.
And the scale, the symmetry breaking scale, is just that of the transverse. It's just a universal thing, rotating.
Yeah, it's really important that the other things don't contribute to get the Schwartzian. But to get the general thing that only this part contributes, you could have evaluated the whole thing.
You could have.
You would have be guaranteed to get it right, but to get it from a Schwartzian, you needed the other thing.
Yeah.
Okay.
You'd get it right, but then there'd be a lot of stuff which would be higher order and so on, if you were keeping that stuff. Yeah.
So you get Schwartzian, so the theta modes. I mean, it would look to me like there is T, R, and theta left over after you have come here. So what happens to the theta degrees? There's some gap develops in the theta degree of freedom.
Yeah, they all contribute at higher order.
Yeah.
To the symmetry breaking.
Yes.
So if you're just interested in the lowest behavior in one over J, then it's just the transverse sphere and the metric degrees of freedom. And that dynamics is then captured.
I mean, it's one way to think of it. You write metric in a particular coordinate system, and things that move the tip around blow up.
Yeah.
Only those things.
That's it. That's
Yeah.
the way I do it.
Yeah, yeah.
This is the reconstruction.
Yeah,
of it,
yeah,
but
yeah.
that's right. So actually, Upamanyu showed that metric. Did you show the finite temperature deformation?
Which
You had the ADS2 form. Just show that. So
Yeah.
there's a sort of ADS2, and there's a finite temperature deformation
mission?
of ADS2.
Okay, this is r. This becomes r square minus
What you have
m.
to do is keep that and keep
Yes.
the rest to be what it is.
So now your question is, how does it work? To which my answer is this. Because the proof of the pudding is in the eating, and I'll show.
That looks like the kind of pudding you don't want to eat.
So I'll show that it works by showing how it works by exhibiting explicit examples. Okay, no one admired my alliteration. Yeah, so the simplest example, the simplest non-trivial example that one can consider is the 5-dimensional black hole in ADS with rotations, equal rotations turned on along its two kartas, the two kartas of S3. And the metric has this remarkably simple form, and there's no bad theta dependence. That's
Could I ask one more question?
yeah, sure.
For a Schwarzschild black hole, there's a well-defined tip. What's the situation with the rotations? Is there a well-defined tip or there's a surface?
I mean, there is of course a transverse surface.
Yeah.
But there is a killing horizon generated by a killing vector.
Right.
And that, in the Euclidean case, just becomes a tip, a smooth tip.
And yeah, so in Euclidean case, there's one point where the place goes to zero volume. There's just one point. It's not like
And then there's a transverse S2.
Yeah,
And
I mean,
there's a transverse S2 which is a deformed S2.
Yeah.
But okay, it's got some.
so
volume with some-
this is an R equals 0 piece over here.
So that's the theta dependence you were talking about.
Yeah.
It doesn't go away.
And yes, it just factors out.
Thank you. You're saying even for Schwarzschild, it wasn't one point. It was an S2.
Yeah.
It was an S2. You got it wrong. Yeah. So yeah, it's just a very S2.
Yes. And the low temperature free energy, the excess free energy above extremality for any value of the, let's say, 5-dimensional cosmological constant is given by this formula.
Right.
And the dimensional reduction here is straightforward because all the metric components are just R dependent. And in fact, for example, a Kaluza-Klein reduction over the 5th dimension, over the 5th circle, let's say, which we call psi, gives us Einstein-Maxwell scalar theory in 4D with a scalar coupled to the Maxwell and a kinetic term for the scalar. And a further dimensional reduction, and the final result I haven't shown here, gives a familiar form with let's say phi cube, which is sort of the volume of the transverse S3 appearing before R. And when we just and the argument is here is sort of reminiscent of what happens in the Rn case because of spherical symmetry, and for the JT model thus obtained for any L, we get these following parameter values of G tilde and J. And no surprise, this agrees with the free energy. And now comes,
Sorry,
yeah.
You have done a Kaluza-Klein from 5D to 4D.
Yes, with
So-
I haven't flashed the reduction ansaters, I can show it to you if you like. Yeah.
Fine, but the circle that you have used,
Yes.
that's a non-contractible. Is it a contractible circle, or it's a thing along with some rotation?
Yeah, I mean it's sort of what appears in Hopf vibration. This S2 cross.
Show your previous transfer slide.
So this F4 of R.
Yeah. Okay. So this F4 of R has no 0 at the horizon. This F4 of R is always positive. If,
Yeah. Along the Hopf fiber you turn
Yes.
on a sort of rotation. So it's sort of
Yeah.
Funnels out. But
Yeah. So yeah, this example was considered earlier in literature, but we have shown how the JT model and the and precisely how the JT model emerges in this case. And now the yeah. Yes. Right. Right. I mean, I just flashed an intermediate step just to compare with the 4D case. And now here's the I'll do it in the 4D. And in 4D, we have considered sort of the most general case, a rotating black hole in asymptotically ADS space with both magnetic and electric charges, and see what we can get. So this is the form of the reduction ansatz. Here, this phi is a function of the, I mean, in like the S-wave reduction before, phi is a function of only the two coordinates or the two RT coordinates in the final plane. And here this non-trivial theta dependence appear all over the place. This xi0 and delta theta 0, these are functions of theta, and sorry, xi0 is not a function of theta, and these occur only in asymptotically ADS space. And there's a gauge field in the full space, And the reduction ansatz for the gauge field is as shown on the slide. And you might ask, why did we take this form of the ansatz? The answer is that this is a precise form of the ansatz that respects the near horizon symmetries of rotating black hole. Again, this paper by Sandeep and Ashok will be of relevance. And notice from here, if you, it will be it will probably be quick to for you to see that the volume of the transverse sphere in this form of the metric is just 4 pi phi square, and this is what will couple to the Ricci scalar in the 2D, this volume modulus. And this is the final form of the 2D action. It has R, it has this one scalar phi, and this has two coupled gauge fields. So this gauge field corresponds to the rotation in 4D, and this gauge field corresponds to the 2D electric field, and these two are coupled. These are U1 again.
And they're not going to fluctuate, right?
No, they're not. Yes, and I'm sorry for displaying this monstrously ugly formula, and just to show you that how non-trivial it is. I mean, these coefficients are all very non-trivial. These are the C1 to C7 are the coefficients that are appearing before here. But I wouldn't be showing you something this ugly in a presentation if in the very next slide I didn't show you something beautiful, which is this. All that troublesome tan inverse chi and so on, they just, okay, I'm sorry I didn't mention this. Chi is the value of the A naught over RH, which is the ratio of the this angular momentum parameter over the horizon radius. And the standard procedure, I mean, we have already outlined the procedure before, gives the JT action.
So what else could you have got?
Yeah, that's right.
Because the
Yes.
equation of motion here should give you the correct.
Yeah, I mean, okay, so this gives the correct L2 square, which comes from comparing with, I mean, obviously that's true that there's nothing else that we could have got, and if
That's the power, once you realize
Yes.
it's going to be JT, that's the power, right?
yes.
That's it.
It only gives you the parameters. I mean,
No, no, it gives you
No, I mean,
the
that,
structure. I mean, Shiraz's point was.
yeah, I mean, once you do this, I mean, all these complicated functions, they cancel out in some intricate way to give you the final correct value of the ADS to radius.
Correct. But it's also true that
It's
you should have obtained the correct ADS to radius from the equation of motion.
yes,
There. And
Yes.
so it had to be.
yes, it had to work. I agree. Yeah, there's also boundary now, so I just, I mean, it was not fitting in the slide, so I just wrote this bulk term. And we can read off this G tilde from this part, and from the linear variation of phi, we get the scale J. And notice that this A naught is a function of the extremal values of the electric and magnetic charges. And again, it gives the correct free energy, and by now it's no surprise to any of us. And there's one interesting possibility that actually Shiraz had brought to our attention, which is the superradiance instability of rotating black holes in ADS. As was shown by Hawking and Real in late 90s, superradiance instability might occur if so this value, this particular definition of angular velocity exceeds 1 over L, and in a sort of, I'm saying this in an imprecise way, if the boundary theory rotates faster than light, that's when the superradiance instability occurs. It turns out that in purely rotating 5-dimensional and 4-dimensional extremal or near extremal black holes that we considered, this bound is always met. So these black holes are always unstable under superradiance. However, in ADS, even when they're big, yes. However, in 4-dimensional,
don't get that. I mean, RH, the entropy gets big, but RH doesn't get bigger than L. It's a very peculiar thing.
Because they rotate.
Yeah, because they rotate. Unlike the charge.
yeah. So there's at least in 4 dimensions, there's a way to.
Because if they were big, they would rotate too fast.
Yeah.
That's probably right.
Yeah.
So there's a way to evade this bound by adding sufficient amount of charges to the black hole to make it Kerr-Newman, which is what we have considered. And indeed, there are certain supersymmetric black holes which saturate this bound, which were first found by Kostelecki and Perry. And if we are adding some small mass above to this supersymmetric black hole, I mean, after we add this mass, they do not remain supersymmetric anymore, but while keeping the other charges fixed, the black holes continue to be stable, and this is one of the class. And in fact, kinematic considerations, I mean, just if you are willing to evade this bound, then you can get some larger parameter space of the charge and other parameters. And interesting.
I've slightly forgotten, the supersymmetric ones have a relation between their charge,
Yes.
magnetic charge and angular momentum.
Yeah,
right?
yeah.
And then you can violate that, but
Yeah.
it still continues to be
Yes.
for some.
Yes.
Still continues to be
Yes.
non-
Yes.
non-zero.
Yeah, and in fact, this kinematic considerations show that there's a talk. I'll take at most 5 minutes. Yeah. So should I stop right now or 2 minutes? Okay. Yeah. So, and there exist small stable near-extremal black holes as well for small values of RH, which we can discuss later. And one of the most interesting thing is the possible applications to black holes in the sky. For asymptotically flat Kerr black hole, the parameter J is 1 over RH.
Maybe we can invite them for this.
Yeah. Yeah. So JT model is expected to capture the dynamics well when the relevant frequency scale is much smaller than this scale J. And the classic example of a near-extremal black hole is GRS 1915 plus 105, which has about 10 solar masses, and the rotation parameter is 0.98, so this is very nearly extremal.
But at the moment, you're only talking about the free energy, right?
Yeah. So this is,
Only a hope.
yeah, hope, yeah.
Just as it worked for small temperature,
Yeah.
if it works.
Expected, that's why.
If it works.
Yes,
and
if it works.
Suggestive,
Yes.
it remains to be.
Yeah, so JT could be a reliable approx. So putting in these values, it becomes 10 to the 4 hertz for this particular black hole. And okay, JT model in at least, I mean, we haven't done that yet, but it would be worth exploring if that gives a reliable approximation of dynamics of real black holes in nature. And so that's about it, and this is my conclusion. So the main one of the key points of this was to demonstrate how the JT model correctly captures the leading order thermodynamic behavior for all extremal black holes, including rotating ones, and then by showing explicit examples in 5 and 4 dimensions how they work out. And there are new possibilities on the horizon. When I wrote this, I did not intend as a pun, but later I realized it could be a pun. So interpret this however you like, whether pun is intended or unintended. So that's it. Thank you very much.